Hi, hello everyone. My name is Ron. I'm with my colleague Bobby here. We're both from NVIDIA. Uh, Today we're going to talk to you about running XGBoost training on Spark with GPU acceleration. So we basically have two parts to this talk. In the first part, I'm going to just tell you a little bit about XGBoost itself and two kind of deep dive topics. One is on gradient-based sampling. The other is on learning to rank. And then I'll hand off to Bobby. We will talk about running XGBoost training on the different versions of Spark 2x and Spark 3. Okay, so the first bit, a little bit about XGBoost. Um, if we are, sitting face to face at this point, I'll probably ask you if you have used the XGBoost before. But hopefully, if you're watching this talk, you've had some experience. You have at least heard of XGBoost. It's an open source library you can use to build sort of a gradient boosted decision trees. It's a pretty popular library. It's used in many sort of Kaggle competitions and data science challenges. Um, there's quite a few companies also use it in production for their real products. It supports different kinds of sort of machine learning problems, from regression to classification to learning to rank, which we'll talk about more in detail. And you can even define your own custom objectives, so you can sort of define your own problems and solve it that way. Since this is the Spark AI Summit, a lot of you are probably interested in kind of scaling up your machine learning problem on a large cluster. XGBoost itself has pretty good support for distributed training. You can use it in different cloud environment or Hadoop Yarn clusters. Of course, the best environment to run distributed training is using Spark, but it also supports running on other kind of data flow systems like Flink. So like scaling out to a cluster is one way of kind of training on a large data set, but sometimes it can be very slow, right? So that's where GPU acceleration comes in. With the same size of cluster, but if you add in GPUs, you can potentially do your training a lot faster. XGBoost has GPU support actually for a while now. It's pretty easy to use. So if you're training on CPU, typically you use the HIST algorithm. Is use histograms to build trees. The GPU equivalent is called GPU underscore HIST. So basically, you just need to swap the tree method from HIST to GPU HIST. Off you go, and you can actually see kind of speed up doing training on GPUs. Okay, so now I'm going to dive a little bit deeper into one of the two topics. The first one is gradient-based sampling. So when you're training XGBoost models, or even for any machine learning problems, typically you want to fit your whole training data set into the memory, right? But if you're doing this on the GPU, GPU memory is typically smaller than the main system memory. On the cloud environment in a typical deployment, I think the current generation of GPUs have 16 gigabytes of RAM. But if you're spinning up a virtual instance with just one GPU, you can typically get 60 to 80 gigabytes of system RAM. So you're at a sort of a disadvantage if you want to fit your whole data set into GPU memory. So even when you're spinning up a good sized Spark cluster, um, if you want to fit everything into GPU, it might still not be possible. So naively, what you can do is you say I put all my data in the system memory or on disk, and I will stream my data in during training. But the problem is you have to copy your data over the PCI Express bus, which typically has a much, it's pretty fast now with the current generation, but it's still much slower than memory access, right? Especially compared to a GPU memory, which has much higher bandwidth and lower latency compared to the PCIe bus. So to work around this problem, people have tried many different things. One approach is to sample your data when you're constructing a tree. At the beginning of this tree construction, you can sample your training data and only keep the sample data in memory. So that way you can reduce the size of the data that you have to keep in memory. And then as you're constructing the tree on each node, you can use the sample data instead of the full data set. But the problem is if you're just doing this, with the most straightforward approach, just with random sampling or uniform sampling, typically it would require at least half the data that they have to keep in the sample to get the sort of reasonable accuracy. So you're not really gaining much. Maybe you can double the size of your training data. But if you have, 10, 20 terabytes of training data, it still requires a lot of GPUs and very large cluster. So to improve on that, so one thing we can try is to use the gradients as sort of a measure to do the sampling. So as you're constructing this series of trees in XGBoost, once you finish the previous tree, you can run your training data through the current model to get the output from your objective function, and you can calculate the gradient, which are just kind of the first order and second order derivatives. And then based on the gradient, you can say, I'm going to sample the data with probability, so proportional to the some measure of the gradients. So people have tried different approaches. This one is called a gradient-based one-side sampling. GAUSS. It's used in another library called LightGBM. And more recently, there's a new algorithm called minimum variance sampling, MVS, that was implemented in XGBoost. For this work, we actually implemented MVS inside XGBoost on GPUs. So with this type of approaches, you can reduce the size of your sample and still get a reasonable accuracy. You can go down maybe as low as just 10% of your data and still get a reasonable model. So once we implemented this algorithm, we tested on this synthetic data set we generated. It has 500 columns. The data is kind of just generated randomly. We tried it on a NVIDIA V100 GPU, which has 16 gigabytes of memory. So if you keep everything in memory, for this particular data set, we can fit about 9 million rows in a single GPU. When we enable this out-of-core mode, even if you're keeping everything inside the memory, because we're sort of building the kind of the transform data incrementally, we can still fit a slightly more number of rows, but it's not too much. Once you start sampling, for example, if you just sample 10% of the data, you can get 85 million rows in a single GPU. It's more or less an order of magnitude bigger. You see, in terms of the training time, compared to the CPU, when you're doing CPU training, whether you're keeping everything in core or you're doing this out of core approach, it takes quite some time, right? It's compared to the GPU approach. So with GPU, it's interesting. Even if we're doing just the out of core approach, but without sampling, it's actually slightly faster because we're only doing sort of the incremental data transformation in the beginning of the training, and then we actually keep everything in memory after that. So it's actually slightly faster than just doing the transformation on the whole data set. And then once we start doing sampling, because there's some cost associated with sampling at the beginning of each tree, so the training time is slightly slower. But in terms of accuracy, is actually pretty much equivalent. For some combinations of hyperparameters, we can actually see some improvement in accuracy. And here we show the training curve of out-of-core algorithm with different sampling ratios. You can see they're pretty equivalent. You see some slight drop when you sample like too much, when you go down all the way to like 10%. Okay, kind of switching gear here. I'm going to talk about the next topic, which is learning to rank. So what is learning to rank? I think the good example to think about is search. Right? You go to Google and you type in Spark. I think I just tried this last night. When you type in Spark, there's actually like 500 million results. So the problem is how do you determine which result to show to the user once you type in this query? So the Google, famously has this PageRank algorithm. It's actually not a machine learning algorithm. It's just a kind of a graph algorithm. So based on the sort of incoming link, they try to figure out which pages are more important. So you can also do the similar kind of ranking approach with machine learning using XGBoost. So once you have the pages that kind of related to a query, you can group them based on kind of the relevance or domains, subdomains, etc. And within each group, we can use machine learning to determine the ranking. So with XGBoost, basically what you have is you want to have a sort of a supervised training data set. So you know the kind of relative ranking between any two URLs. And once you have that, then you can sort of iteratively sample these pairs and sort of minimize the sort of ranking error between any pair. So there are the three different algorithms supported on the GPU. First one is sort of the default, just do the pairwise comparison. Then there's two more, mean average precision and normalized discounted cumulative gain. They're just kind of variations on the pairwise approach. It has further weighting of the training instances. To train this learning to rank model on GPU, I guess first you have to enable the GPU histogram method, and the objective function you have to choose something that's the ranking objective. And when you're evaluating the model, it also needs a metric that supports the ranking objective. There's a bunch of different objectives you can use to try to optimize. For performance evaluation, we use the Microsoft benchmark dataset. I won't go into too much details here. You can read sort of all the information on the slides. So the final results, once we enable everything on the GPU, you can see with all the three different algorithms, a GPU is a lot faster, 10 to 20, even like close to 30x than the equivalent CPU approach. Now I'm going to hand off to Bobby, who will talk about running XGBoost on the different Spark versions.
Thanks, Ron, for the introduction of the XGBoost internal things. From our talk, we can see actually a pretty big speed up on learning to rank by leveraging GPUs. It's actually 20x speed up. That's quite amazing. But what I would like to see is we can not only get good speed up from learning to rank, but also we can get good performance from classification and regression provided by XGBoost by leveraging GPUs. But how to use XGBoost to train on our existing data? The first thing I think we may need to do is converting the existing data to the numeric data, which is the only data format accepted by XGBoost. But in reality, our existing data may not be numeric, which means we need some tools to do the ETL. But the question is, which tool? Yeah, I guess you have guessed it's Spark. I suppose you have the knowledge of how popular Spark is and how powerful Spark is about doing, ETL things and other things. So I don't want to talk much about why Spark. Fortunately, XGBoost community has supported XGBoost on Spark in XGBoost 4J Spark project. XGBoost 4J Spark project, I mean to integrate XGBoost and Spark by fitting XGBoost to Spark's machine learning library framework. So with the integration, you can not only uses the high performance of XGBoost, but also leverages the powerful data processing engine of the Spark. So user can benefit a lot from the XGBoost 4J Spark project. But looking at the whole machine learning workflow, if you are working on machine learning, you probably know training models and doing predictions, that's pretty small portion of your whole work. Most of your time will be spent on the data preparation. Just like the picture shown, on the left, you have the traditional CPU-powered workflow. Data engineers start in the morning by writing some code to load the data engine to do feature cleanups. They started it running on a big data set. Then they go and get some coffee. After a while, they realized, oh, I forgot to add a feature, so I need to change my code a little bit and restart it and wait. Another while, there were unexpected long values and some missing data somewhere. So I need to change the code and restart it again. So it's not just a fire and forgot process. It's actually an iterative process. All these things like together, are pretty slow because you're not leveraging GPUs. So how do we solve this problem? And how do we accelerate ETL by GPUs so we can have a faster end-to-end machine learning workflow? Yes, Rapid cudf is a solution. Actually, Rapid cudf has two components, libcudf and language bindings. libcudf is a CUDA++ library which provides low-level APIs to accelerate various data frame operations like sorting, filtering, joining, aggregation, group bys, and so on. And on top of that, different language bindings for Java, for Python. So, with Rapid cudf, we came up with a solution to accelerate XGBoost end-to-end on Spark 2. First, we load the data into the GPU memory. And second, the GPU memory resource is pretty precious, so we need to ensure to load more data as much as possible. The chunks loading can achieve this goal. The third is converting the cudf columns to the sparse row-based DMatrix. And finally, we fit the DMatrix to the XGBoost and train and get the model. And this sliding is demonstrating how to train XGBoost for both CPU and GPU. The left code is for the CPU pipeline. First, we need to load the data to the data frame, and then we need to vectorize features. And finally, we fit the data frame to the XGBoost classifier or XGBoost regressor. On the right code, you can see we customized the GPU data reader to load the data into GPU dataset. and we skipped the features vectorize because we already load the data into the GPU memory with column format. Instead, we specify the features column lengths when building DMatrix. And finally, we fit the GPU dataset to the XGBoost classifier or XGBoost regressor. And we did some benchmarking for multi-gauge data, total 190 gigabytes. You can see from the chart, the shorter is better, obviously. We have 34x speed up in training time and 6x cost saving. That's quite a significant number. Before talking about XGBoost on Spark+3, if you remember, we have a customized GPU data reader and a GPU data set to bring cudf to accelerate XGBoost on Spark+2. We cannot directly use data frame of Spark. That's because of the poor GPU support on Spark+2. But as Spark+3 is coming with GPU scheduling support and columnar processing on GPUs, so it is possible for Spark+3 to be accelerated by GPUs. Actually, we did this in a Rapids plugin project. Rapids plugin actually is Apache Spark plugin that leverages GPUs to accelerate processing while Rapids libraries, for example, cudf, RMM. So with Spark+3, so with Rapids plugin on Spark+3, there are no any code changes. This is something that happens behind the scenes. In our initial release, Rapids plugin can be used to accelerate Spark data frames, Spark Circle, and machine learning, deep learning training frameworks. And this is kind of we've designed. We've been working on to make this happen. Actually, there are two separate plugins we provide. The first is computation ETL plugin that works with Circle and data frame APIs, and the other is Shuffle plugin. But I don't want to talk much about the Rapids plugin because we have a narrow session to cover this. So I strongly recommend you to watch that session. So with Rapids plugin, we can accelerate the XGBoost end-to-end by GPU scheduling, GPU accelerated data reader, chunks loading, and what's more, the operators can also be accelerated by GPUs. For example, filter, sort, joining, and so on. Yeah, from the code, you can see we use the built-in data frame of Spark to load the data into the GPU. And we also skip the feature vectorize because the Spark native reader has loaded the data into the GPU memory with columnar format. And we also specify the feature column lengths to XGBoost classifier or XGBoost regressor. And finally, we fit the data frame to the XGBoost classifier. And we also did the benchmark for Criteo data total 1 terabyte. We have 5.5x speed up in training time and 6.4x cost saving. And we provide a new ebook, Accelerating Spark+3. In this book, you will learn about the data processing evolution from hardware to GPUs and the NVIDIA Rapids library. And what is Spark, what it does, and why it matters. something about the GPU acceleration, data frames, and the Spark circle, and examples of an end-to-end machine learning workflow GPU accelerated with XGBoost. And here are some links for XGBoost. So I think this is the last thing we have. Thank you.